Thank you so much for the opportunity to share. And I have a very different approach that I'm often have a hard time seeing the forest for the moss and mushrooms. So I'm going to be taking you through the details of some of the observations I find intriguing. And in particular, very interested in the nitrogen component to the organics. And that may tie in with Dale's interest in the nitrogen in the tholins and how that gets to be so nitrogen rich. Well, I should thank my recent discussion mates, Rhonda Stroud and Cecile Ingrand, and also my two co-authors, Hope Ishii and Mike Zielinski, on a review paper that I put together that gave me a context to continue these assembly of facts and trying to put a story to it. So I wanted to first just define what I'm going to be talking about, which is I'm going to be talking about the refractory organics in comets. That's the material that has, I presume, a very long lifetime in the coma. It may be related to solid state material that has a limited lifetime in the coma, but we don't get the chance to see that material delivered to Earth or probably collected by spacecraft. So particularly talking about the material that's robust, I will mention the labile or soluble organics briefly. So my interest is trying to context this material as to whether it could be from the interstellar medium or from cold cloud environs. And I think that that's a very difficult task. I have one particular sample I'm going to talk to you about I think actually really distinguishes that there has to be two epochs of formation. Because the cold cloud environs for a dense cloud and the protoplanetary disk, outer disk have similar temperatures, perhaps similar densities, but have different time scales. And also, as Yvonne mentioned, material can be lofted into the radiation field of the sun and provide energy for chemistry to happen. And that exposure to the ultraviolet light due to particle movements in the outer disk may actually perhaps lead to more efficient processes than the dense cloud, where the timescales for particles to reach the outer part of the dense cloud and get some energy necessary for this chemistry are much longer. So I'm going to talk about that. I'm going to show you examples of that some organic materials have textures and structures that require multiple processing events in different environs. And the idea I want to put forth today is to talk about not necessarily that you have material from a primitive body, but I think comets are showing us that you have, comets and some meteorites are showing us that it's the diversity of composition that may give us clues to that it really is primitive, because the minimum of aqueous alteration starts to erase diversity on the nanometer scales. And in comet materials, you see diversity, that is materials that had to have formed in very different chemical environments and at very different temperatures right next to each other on the nanometer scale. And to me, that means that that material hasn't received post-processing. So you're seeing it since it was held in the archive. So first I'm going to talk about the carbon to silicon ratio. And this is not measured in very many bodies. So the simple diagram on the left side is from a nice paper by Frey et al., 2017. And what you see is that basically as you go from the sun on the left-hand plot, carbon to silicon atomic ratio versus for a few different bodies, you have the sun, Comet 67P is a little bit less carbon to silicon, Halley is a little bit less, and chondritic porous interplanetary particles, they're also called CP-IDPs, and that are the best analog for comet particles, are a lower abundance. But I want to point out that, so there seems to be a trend between different kinds of bodies, that there's a range of carbon abundances. But I want to point out that, for instance, the CP-IDPs haven't been measured in the bulk since the 1990s. Since that time, they've been trying to collect them in a foam-type material instead of on silicone, a silicone gel-type substance, which could hamper the silicon ratio measurements. But the work that was done was really phenomenal in that it showed that the carbon weight percent in what are thought to be cometary particles, the figure on the lower right, spans from 5 to 25 weight percent. And after this article in 1994, they published LPSC abstract that indicated one had 45 weight% carbon, which is 90% by volume. So the first message here is that the range of material in cometary particles is huge compared to what we see in meteorites. That some of these particles are indicating that some materials had a lot of carbon. And the second thing is in the lower left, you see the pie-type wedge diagrams from the Rosetta Cosima instrument that show you by an atom and weight% what the different solid state materials are, that is the dusty materials, and they find that about 50% of the carbon atoms are in a high molecular weight organic solid material. So that means that this particular body captured a lot of carbon that had gone through some kind of organic formation process and was very robust. And so what I show in the next slide is just that you have to look at the sources to understand the range of measurements. So for instance, if we look at Halley, it depends upon which paper you look at. If you look at the Jessberger paper from 1988, you see the higher measurement of carbon to silicon ratio of 4. But if you look at the Lawler and Brownlee paper, did a reanalysis of the high resolution mass spectra, they find that actually you get, only for the smallest particles do you get a ratio of 1. So that depends upon which instrument and how that data was collected. And I'm making a point here that the smaller particles are like 5 to 10 nanometers. So when you get to the smallest particles, there's more organic material. The carbon to rock material, or carbon to silicon ratio, is more like 1. And also that there were very few just organic particles. Most of the particles were mixed, and they also think that's true of the Cosima measurements from Rosetta. So the question is there a carbon to silicon gradient in the solar system? And I think it's still a small number of statistics, and how were those measurements made? Were they on bulk particles? And what kind of processes did those particles undergo on their way to our measurement capabilities? Did they suffer some loss of organics in the atmosphere of the Earth? So for instance, here on the right-hand side, the left-hand side, you're seeing a similar plot to what I just showed you, but a new sample of what are thought to be either cometary or some other primitive body, ultra-carbonaceous Antarctic micrometeorites, UCAMs. And the UCAMs have a very high carbon to silicon atomic ratio. They can be 90% by volume carbon, and it's organic, an IOM-like material, but very nitrogen rich. And the UCAMs are thought to perhaps come from some kind of outer body because their nitrogen is locked up in a very different kind of material. And 67P is kind of given by the oval. So there is an indication, but again, you have to think about how the materials were delivered. And the UCAMs are unique in that they're big enough, they're about 300 microns in size, and so they float down in the atmosphere compared to smaller particles, and therefore they don't get as heated, and they seem to have preserved more of their sulfur. That was mentioned by Kelly. So the next thing of interest to me is the nitrogen to carbon ratio. In meteorites, as I'll show in a moment, the nitrogen to carbon ratio is 0.02 to 0.03. In Comet 67P, it's ranging from 0.02 to 0.06. And I show the panel on the far right, kind of showing the histogram of the measurements of 23 particles compared to carbonaceous chondrites in the green, in the middle panel histogram, and ordinary chondrites. So you can see a selective diminishment in the amount of nitrogen in the organics as you go to more processed bodies in the solar system. But I also want to point out that there's a new measurement of 2 interplanetary dust particles that are very GEMS-rich, glass with embedded metal and sulfides. It's a very easily destroyed glassy material. And there seems to be 2 reservoirs, a 0.03 and a 0.07 reservoir of nitrogen to carbon. And they come in different parts. The nitrogen that is less enriched is in nanograins and in the matrix of the IDP, and the higher nitrogen is in blebs, rims, and is thought to be more primitive. And then I mentioned the UCAMs that have a much higher nitrogen to carbon ratio, and the bottom right plot shows you that. It's a clear distinction between one particular UCAM and the other carbonaceous chondrites, orgae, and another UCAM. So I'm going to skip this one. Basically, that's talking about the possibility of volatile loss and why they think the nitrogen comes from the outer solar system. But there's 3 different kinds of organic matter, some with glassy silicates, some associated with mineral crystals, and some that's just associated with dusty patches and nitrogen-poor organic material. So here I'm introducing on the right-hand side, very interesting method to look at the organics. You look at basically the relative contributions and identification of the bonds in the material using X-ray absorption near edge spectroscopy. And what's identified there is particular feature C-triple-N, which is very important for prebiotic molecules and is very clearly seen in 2 of these UCAMs. So here's just, again, another kind of way you look at organics. This is a mass spectrometry. On the left is the 67P measurements and the repeated peaks that are showing up on the right-hand panel that are different amounts of CH, CH2, CH3, and the left-hand panel, which has a higher atomic number, that's a signature of high organic weight in the organic material. That is, everything is very strongly bonded so that the material itself is coming through the mass spectrometer in a big, massive chunk. And so the bottom 2 of that left-hand panel are carbonaceous chondrites, and the top 2 are 2 of the particles, and the spectra look very similar. So to recap, 67P has a lot of carbon, high molecular weight organics, and they're most similar to the primitive carbonaceous chondrite, insoluble acid, insoluble organic material. And yet they still have a higher hydrogen-carbon ratio and higher nitrogen-carbon ratio, and carbon to silicon is higher than in haligen and CPIDPs. And I mentioned this again, that basically half of the material is in this high molecular weight organic material. I want to just throw out that Rosina, the gas phase instrument, also sees soluble organic material with amino acids. This was due to a large dust particle hitting the spacecraft during a close flyby. They got a huge signal on many different species, and they were able to see so a small amount of these functional groups, the COOH bond, and otherwise that material, the COOH material, was not seen in the solid state materials. So what is this insoluble organic structure? This is a wonderful diagram put together by Yvonne and Luella Mendola in 2002, and what you see is these aromatic domains of these cyclic molecules, the PAs, connected with aliphatic chains. And the length of the aliphatic chain, if it's got a terminal end, it'll have three H's, and if it's just a long chain, it'll have a lot of H's up and down, and so that's the CH2 to CH3 ratio. If you have a lot of CH2 to CH3, then it's a long chain because you have a lot of up and down, bonds like on a railroad track compared to the ones at the ends. So this picture actually holds up pretty well when you look at meteorites. This is the Zane spectra on the left-hand side of the figure of meteorites showing the bonding structure, and what they find is that there's a predominance of like 3 aromatic rings in a row or connected together that are part of the structure. It's kind of a predominance of 2 or 3, not really long aromatic domains and not single benzene rings. For me, I want to point out that the Zane spectra, even though the meteoriticists think that there's a lot of variety, there's just, to me, a tremendous amount of similarity between these different kinds of meteorites, because I'm going to go on to show you what the Zane spectra look like from cometary samples, as well as the one I just showed you. So just also note that 40% of the carbon is lost in how they prepare the samples for study. And also, if you go and read this wonderful paper by Connell Alexander, you'll find out that they do all kinds of horrible things to the IOM. They heat it and bombard it, and it still manages to survive quite a bit. So here's in comparison, I'll just go backward and forward. You see the types of bonds you see for a lot of the aromatic rings in the meteoric material. But here you see aromatic ring materials with CH, O, nitrogen substitutions, and this triple bond N group. So there's a greater diversity of bonding structures in the very few numbers of samples that have been studied by stardust. I mean, relatively few compared to meteorites. If you go on and look at these two particular IDPs that I'm going to highlight that have a lot of this C-triple-N bond, basically I have 3 slides on this particular set of IDPs because I think it's the first evidence that convinces me that there's multiple generations, at least 2 stages of formation. So there's higher density organics on the rims of the gems and also inside the gems. So the gems are a glassy material, and it's highly debated whether they are a very rapid quench product from the solar nebula or whether they are grown in the molecular cloud phase of the interstellar medium. I'm going to say right off, I have a strong favor for the growth at cold temperatures because there's experiments that show that's viable. And secondly, the lifetime of interstellar grains is way too long to explain. I mean, it's too short. You sputter them away and destroy them, and you would not see dust as abundantly in the interstellar medium unless you had some way to reform it. And this is called the cold condensation model. For many years, I was much a skeptic, but this kind of material and this particular 2 particles, very convincing to me. So there's a lower density organic matrix, and the nitrogen concentration in that matrix is less. So the analysis indicates that this layered texture, where you have on the bottom right, you can see there's a lot of organic in red, and magnesium, sulfur, silicon, and iron make up the blue and greenish colors. The sulfur is yellow. You can see that this is a mixture of organic material and this glassy material that is not any mineral-like material you would commonly see in chondrules or in many meteoritic samples. So they were able to use a 4 nanometer scale examination of this material. And what they see is that they see actually nanoglobules of this organic material, and I put some arrows. They see this glassy material like growing like a rim on this dense nitrogen-rich organic nanograin. And to me, there's no way you could ever do that with condensation. You have to grow the material, because first you've got the organic, and then you've got the silicate on top of it. So the title of the paper, Multiple Generations of Grain Aggregation, they suggest that the higher nitrogen content organic, it's also denser, formed first, and perhaps formed in a colder environment. So the conclusions to the study is that these gems formed in a region where nitrogen-rich organics formed and survived, that is cold plus radiation. The 15 to 14 nitrogen enrichment strongly supports they formed in an interstellar medium environment, that is a molecular cloud environment. And the authors state that the organics would be destroyed at 450 Kelvin. And so all these, every aspect of these particles means that they never were heated beyond that. And there's other experiments that show that if these particles are heated to about 1,000 Kelvin, that these glassy materials would be transformed into iron-bearing olivine crystals, and they're clearly still disordered. So the next step is just to show you, yes, there is definite ISM heritage in some particles. These were collected in the stratosphere when the Earth passed through the 26P Greek Skeller comet stream of particles, and they have large deuterium to hydrogen hotspots and 15 to 14 nitrogen hotspots. And they also have quite a few original force-straight particles from AGB stars. But again, the survival of that material directly from stars into these primitive bodies, or these bodies that haven't been reprocessed, is still only 1% or so. To me, what's intriguing is that the deuterium enrichments are out of this world. I mean, I'm reading the plot in that it's an individual has 20,000% or 20 times the DH ratio as standard mean ocean water. So the deuterium to hydrogen enrichment and the 15 to 14 nitrogen enrichments are both thought to occur because the bonds for the heavier isotopes are deeper, and so when those atoms hit a cold interstellar grain, they tend to stick and form and get stuck in and are transformed into organics. So those are signatures of cold cloud processing. So this gets into the realm that Yvonne was talking about, infrared spectroscopy, just to show you that there's a whole other way to look at this material, and it shows diversity as well. This shows the diversity of bonds on the left-hand side, depending upon what wavelength you're in, all the way from stretching modes to bending modes. And in particular, on the right-hand side, what different kinds of base materials, like are you looking at a carbon attached to an aromatic, a hydrogen? This is the hydrogen stretching region. You know, where it's, the frequency of the stretch depends upon what the hydrogen is attached to. And so spectral analysis is very powerful in being able to identify peripheral groups. This is the meteoritic in IOM in the infrared, and I highlight that there are some interesting data pertaining to potential JWST observations in the 5 to 8 micron region, which we haven't been able to do for a long time, or we don't have sensitivity yet. So yay, JWST, let's hope that we get some great discoveries. But I made a circle around the 3.4 micron region, and as a spectroscopist, yes, they have different contrasts, but they all have very similar, roughly similar spectral features compared to the comets. So the comets show a greater diversity in the relative amounts of CH2 and CH3 bonds. And I show this, this cross study between the Zane spectra and the infrared spectra. And I also show you a couple of IDPs studied by Graciela Meltrat. And this particular one, Chaka, has very strong aliphatic bonds. That does not, the spectrum on the right-hand side where I put the arrows doesn't look like the galactic interstellar medium. There's very strong CH2 dominated regions of the spectrum. And then there's another particle, FIBO, which is a fine grain material, and is 3.4 microns, very different. So it's worth going, if you're interested in the spectral resonances and what they tell you about the materials, these papers are fascinating because they talk about the texture of the material and the different amounts of long chain versus short chains. So this is the suite of resonances that have been studied, and this is the CH2 to CH3 band depth ratios. So if you have a bigger number, that means it's a longer chain. And you know, in some ways, as far as I understand from being coached by Yvonne, a more fragile molecule. And so if you look like 2/3 the way down the list, you see like 4.6. That's the IDP Chaka. And FIBO, 1.96. ADA, 4.3. So that's basically much higher or much more greater abundance of these more fragile longer chain molecules than in the interstellar medium. So this is my summary. It's a wide variety of abundances of carbonaceous matter between cometary particles, spanning little to 90% volume. Refractory carbonaceous matter can be a separate or mixed component at the nanometer scale. Diversity of compositions down to nanometer scales are seen. The structures are rims, vesicles, matrix, each with different properties. Their organics are destroyed or desorbed at 450 Kelvin, or we need more experiments to assess this range of temperatures. We kind of know a little bit from when we see materials released from solid grains in the comey. We see these distributed sources, that is the dust distributing the gases into the cometary comey. We have a little bit of evidence of that perhaps in the Halley flyby, although it depends upon more scrutiny. But there are lab samples of comet return samples from IDPs, UCAMs, and giant IDPs that indicate that organics can be modified. Like if you have a microprobe, you have to be very careful that you're not actually, or you're doing Raman spectra, that you're not actually changing the material while you're measuring it, because you're depositing a lot of energy as you're measuring it. So there's special techniques now to try to have good thermal conductivity of the sample or have a very short dwell time. And I think that comets provide the only collectible sources of these more diverse organics, and they're very important to compare with the meteoritic material. So the nitrogen to carbon ratio, oxygen to carbon ratio, and hydrogen to carbon ratios vary, and vary more than the range of variation seen in meteoritic IOM. There are insoluble organics that are strongly similar to the bonds in meteoritic IOM, but there's a greater variation in different regions of the same particle and between particles. So a meteoricist will talk to you about the great variety of structures in IOM, and I'm telling you comets have a lot more variation of structures, and that difference is important. It's telling us something about how well the material survives thermal processing, or perhaps a greater influx of materials that wasn't as processed. So homogeneous or homogeny sometimes exists in regions of a particle or only between dispersed components. It exists at some size scales within a single particle. It's lacking at 4 nanometer scales in this GEMS-rich IDP, but exists between the components. So it's telling you a little bit of a hierarchical aggregation of this material. The soluble organics carry PAWs and amino acids, and some carbonaceous matter is solely elemental carbon and may form via non-organic pathways. So thank you for letting me share all the details, and hopefully you now have a basis for which to understand that COMET samples and meteoritic samples both are an enriching way to try to set a context for our studies of surfaces of our outer icy bodies. Thank you.